5. Bernoulli and energy equations. Welcome to one of the most powerful tools in fluid mechanics, Bernoulli's equation. This is where theory meets real-world applications. Whether it's an aircraft wing, a leaking tank, or blood flowing in arteries, Bernoulli helps us make sense of energy transformations in moving fluids. In this session, we'll unpack what makes Bernoulli's principle so widely used. You'll see how pressure, velocity, and elevation relate through a simple but elegant equation. Then we'll extend this into the general energy equation, your go-to formula when dealing with pumps, turbines, and head losses. Think of this chapter as the bridge between intuition and engineering calculation. Let's get into it.
1. Introduction. Let's set the stage. This chapter introduces three of the most essential equations in fluid mechanics, equations you'll keep coming back to throughout your engineering career. First, the mass conservation equation. It's the backbone of fluid flow. What goes in must come out. Then comes the Bernoulli equation, which links pressure, velocity, and elevation, ideal for understanding energy transformations in frictionless flow. And finally, the energy equation, a more general version that accounts for mechanical devices and losses. These aren't just formulas. They're the foundation of real applications like pumps, turbines, wind turbines, and flow analysis. Master these, and you're well on your way to analyzing complex fluid systems with confidence.
2. Conservation of mass. Let's begin with the foundation of all fluid flow, the conservation of mass. In steady flow, what goes in must come out. That's the idea behind mass flow rate, where m equals rho VA stays constant along a streamline. When dealing with incompressible fluids, the continuity equation simplifies nicely. V1A1 equals V2A2. This tells you how velocity and area interact. Reduce the area, and the flow speeds up. The more general mass balance for a control volume is straightforward. The total mass entering equals the total mass leaving, or sigma m dot in equals sigma m dot out. These equations aren't just theory. They're tools you'll use for analyzing piping systems, turbines, and even heat exchangers. Once you grasp this, you're ready to tackle real engineering flow systems.
3. Mechanical energy and efficiency. Here's where we break energy down into pieces you can actually use. In fluid systems, mechanical energy comes in three forms: kinetic, potential, and flow energy. Think of them as the motion, height, and pressure effects in a moving fluid. But real systems aren't perfect. That's where mechanical efficiency comes in. Whether you're using a pump, turbine, or motor, not all input energy gets converted into useful work. Efficiency helps you measure that gap. For example, a pump's efficiency compares the useful mechanical output to the shaft power input. A turbine's efficiency flips that, how much shaft work you get from the fluid's mechanical input. And for motors, it's about converting electrical energy into shaft power. Knowing these formulas helps you diagnose performance and design systems that actually work, not just on paper, but in practice.
4. The Bernoulli equation. Here's the superstar of fluid mechanics, the Bernoulli equation. Simple in form, powerful in application. It says that for a steady, incompressible, inviscid flow, the total mechanical energy per unit mass, pressure, kinetic, and potential stays constant along a streamline. But to use it well, you need to understand pressure in all its forms. Static pressure, P, is what you feel when the fluid isn't moving relative to you. Dynamic pressure, rho V squared over 2, reflects the energy of motion. Hydrostatic pressure, rho GZ, comes from elevation. Stagnation pressure is what you get when a moving fluid is brought to rest, used in pitot tubes. Now, a word of caution. Bernoulli has limits. It only works along streamlines and assumes no viscosity or compressibility. So don't apply it where friction matters, like boundary layers or swirling flows. Despite this, its applications are everywhere, from measuring flow speed with pitot tubes to analyzing nozzles, pipes, siphons, and pressure drops. It's one of the most elegant tools you'll use if you respect its assumptions.
5. Energy and hydraulic grade line. Now, let's visualize energy in a flowing fluid. The hydraulic grade line, HGL, shows the sum of pressure head and elevation head, basically how high the fluid would rise in a piezometer. Think of it as your fluid's visible pressure. The energy grade line, EGL, adds one more layer, kinetic energy. That's why it always sits above the HDL by an amount equal to V squared over 2G. EGL represents the total mechanical energy per unit weight of the fluid. Here's a key insight. In a perfect frictionless system, the EGL remains flat, no losses, no dips. But in reality, as friction kicks in, the EGL slopes downward, revealing where energy is being lost. HGL and EGL help you read the energy story of a system just like reading a topographic map for fluid behavior.
6. General energy equation. Now we go beyond ideal assumptions. The general energy equation is your all-in-one tool for real-world flow systems. It's based on the first law of thermodynamics and accounts for more than just mechanical energy. Unlike Bernoulli's equation, this form includes energy added as heat, Q, energy exchanged by mechanical devices like pumps or turbines, WSHAFT, and energy loss due to friction, HL. It works for any steady, single-stream flow, and it tells the full story: thermal, mechanical, and frictional effects together. This is the equation you turn to when things get messy. Whether you're designing piping systems, analyzing HVAC units, or evaluating turbines, this equation captures all the moving parts. It's not just elegant, it's essential.
7. Applications of Bernoulli and energy equations. This is where theory meets engineering practice. Bernoulli's equation isn't just for exams. It's used every day in tools that measure and control fluid flow. To measure flow rate, devices like Venturi meters and orifice plates apply Bernoulli's principle. They detect pressure differences and translate them into velocity and volume flow. Pitot tubes go a step further. They measure stagnation and static pressure directly to calculate velocity. When it comes to machines, Bernoulli's and energy equations are essential. The pump head equation helps size pumps based on pressure differences, velocity changes, elevation shifts, and friction losses. Meanwhile, the turbine power output equation tells you how much work you're extracting from fluid energy, factoring in efficiency. These aren't just formulas, they're your blueprint for analyzing and designing real-world systems.
8. Summary. Let's wrap it all up. First, mass conservation tells us the flow must balance. Whatever mass enters a system must leave or accumulate. Then Bernoulli's equation connects pressure, velocity, and elevation, assuming ideal flow. But when reality kicks in, the energy equation steps in to account for added work, heat transfer, and frictional losses captured by head loss, HL. To visualize this energy distribution, we use EGL and HGL, lines that track total energy and pressure levels throughout the system. Together, these concepts are used in real-world applications like pumps, turbines, siphons, and flow meters such as Venturi and pitot tubes. So whether you're analyzing a pipeline or designing a turbine, these equations are your starting point for turning flow into function.